talk about isomeric states of materials. And specifically this kind of concept that we can have materials that are compositionally identical but structurally distinct. So one of the best examples of this is the horrific tragedy of thalidomide. So thalidomide was a drug that was given to women to ease morning sickness in the 1950s and 60s. Thalidomide, probably spelling this incorrectly, but you can kind of Google that and check it. Thalidomide comes in kind of two forms. So it's a left-handed form and a right-handed form. Both of these are compositionally identical, but structurally distinct. Now, one form of this drug is able to kind of ease morning sickness. But if the other type of the drug, the other-handedness, so it's like left and right-handedness, in terms of structure, one-handedness or one type of one structural distinct form of that drug will actually cause horrific birth defects, neurological diseases, and a lot of horrible, other horrible kind of side effects. So one of the key things about this lecture and isomeric states, and actually this lecture in general, is this whole idea that structure dictates properties. And again, you can see kind of the horrific effect if you don't know the structure of those materials. So that left-handed, right-handed form, it could cause very, very serious problems. So that's kind of hopefully the sobering kind of motivation for this particular lecture. But there are definitely different types of isomeric states of material. So let's first talk about isomers versus conformers. So isomers are molecules which are compositionally identical but structurally distinct. Conformers, on the other hand, they're not isomers, are related by rotations about a single bond. So they are not, so conformers are also chemically identical, but they are not structurally distinct. You can relate them You can relate them about a rotation about a single bond. So let's go ahead and actually you can see lots of different types of isomers. Hopefully you've heard about cis and trans. These are probably new that we're going to introduce today: isotactic, syneotactic, atactic, stereoisomers. They're also structural isomers, sequence isomers, lots of different types of isomers. The key idea here: structurally distinct, compositionally identical molecules. Conformers are related by this rotation around a single bond. Now, why do we say this rotation around a single bond? Well, because at room temperature, again, due to these secondary or intermolecular interactions, those are breakable and reconfigurable at room temperature because their bonds are less than 1 kT. So a molecule like this, for example, so let's just say that this is C, H, 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 and then this is C, H. Actually, excuse me. Let's call this, let's call this H. I'm going to call this Cl. I'm going to call this, actually, keep that H, H, H. So this molecule and this molecule, which is exactly the same, I'm going to switch my Cl, H, C. I'm going to call this Cl as well. Excuse me for that. Switches here, Cl, H. These are conformers because I could relate this and just rotate around basically a single kind of bond here. So I could rotate one of those molecules, and again, they could look actually structurally identical. So that's kind of the key aspect. I could do that kind of rotation there. I could flip them. So I could rotate around the single bond, and I could recover these states. But because I could rotate around a single bond at room temperature. But at room temperature, thermal rotations about a double or triple bond are essentially zero. So these, if you have a double bond, they're fixed. You cannot move, you cannot rotate around them. So that is not possible. So these molecules, dichloroethene, here and here, again, compositionally identical, just like this, but we can't rotate around here, so these are fixed. So these are, while these were conformers, these are isomers. And specifically, they are geometric isomers, and they are, basically, this is going to be our cis, and this is going to be our trans. Why is it trans and cis? Cis, same sides, are chlorines. Here, trans, across. So just kind of, again, hopefully a little bit of a reminder from chemistry. But again, that is one idea. It's a structural isomer or geometric isomer, and the cis and trans conformations. bond prevents it and makes it structurally distinct. Those are two structurally distinct molecules. We can't rotate around them and relate them by a rotation. So, stereoisomers. Basically, if you have some type of ordered, let's call this, let's say, so it's H, and I have some distinct structural group, so R1. I can arrange R1, C, H, R1. These are isomers, these two molecules, even though, again, they're exactly structurally the same. R1, H, and C, H, R1. And I could have a completely, so there's some kind of, again, down, up, down, and it would repeat. And you could kind of have some random one like this, R1, H, C, R1, H, C, R1, H, and then R1, H, and et cetera, et cetera, et cetera. And there could be kind of chaos and random. So these types of isomers, again, compositionally identical, except for, again, ignore that guy, it just repeats. Compositionally identical, but structurally distinct. So if these pendant groups are all arranged on one side, this is going to be an isotactic material. If there's kind of some periodicity, some sequence to them, the rotation or the kind of location of these pendant groups is symbiotic. And if they're completely random, like we kind of see here, that is going to be an atactic isomer. Now, we talked about previously, especially for polymers, that polymers depend on these van der Waals interactions, or these intramolecular interactions that are very, very weak, but the force decays is d to the -6. So when you look at these polymers here and this tacticity, we want to kind of be able to stack polymers close together. So because if we stack them close together, this distance decreases and our force increases, and that polymer will become much more stiff or have a higher melting temperature, et cetera, et cetera, et cetera. So which of these forms can stack most efficiently? Well, it'd be isotactic, right? Because I can stack here, here. I know where all those side chains are, so I could kind of arrange that so I could pack these efficiently. I can't stack like a molecule here and overlapping because, again, they can't occupy the same distance. So syneotactic is going to be a little bit harder, but that'll be kind of first best stacking, second best stacking. This atactic is completely random, so I have to kind of put a lot of distance because I have to kind of think about these pendant groups on the side there. So this is the worst one, the third best packing, or worst packing. So this will have the lowest melting temperature here. This will have the highest melting temperature here, assuming everything else is the same. You can also have sequence isomers. So block copolymers can be designed as A, B, A, B, A, B, A, B, or you could have a single block. But again, chemically identical, structurally distinct, and they have vastly different properties. You could look up some research by Professor Charles Singh at the University of UIUC, formerly of the Alexander Krapps group at MIT, and he does a lot of work with these kind of block copolymers and these sequences. So one last thing on this lecture, and then we'll kind of call it a day. So in addition, conformers have this really, really unique property. So conformers, again, we can relate, these aren't structurally distinct states, but they have kind of these different rotational states. And we call these rotational isomeric states, RIS. And we'll show in the lecture this Mathematica notebook. But those rotations, here we're kind of showing a rotation of those. We're looking at a polymer like this. C, C, and then we have basically we have CH3, we have H, H, let's just do CH3, H, and H. So we could rotate around this single bond, and you could kind of see these energy states, right? Why is this energy state the highest? Well, because I have this big bulky group, you could see, right next to this other big bulky group. Why is this state the lowest? Well, because the big bulky groups are the farthest away. These are our trans configurations. So you can kind of identify some of these energy states. So you can see that A, the method goes farthest apart, that's going to be our kind of trans states. D is the highest, they're right on top of each other. This is the cis states. And there's also going to be these kind of two other lower energy states as well, where these are these Gauss plus, Gauss minus conditions. You can see that they're apart, but they're not the farthest distance apart here. So they're still moving apart, but they're not, again, they're not completely in that trans configuration. So those are two, this state, these B are called Gauss plus and Gauss minus. Those C states are kind of a little bit, again, there's still some kind of eclipse kind of happening. There's still kind of kind of on top of each other. So you can kind of see here this eclipse conformation in C. Again, there's a Mathematica. This actually, if you look at the citation, there's this Wolfram Mathematica demonstration that I'll kind of show in lecture to kind of show the rotation, and it's pretty cool. But the key idea here is look at low energy states. That's where we want to be at the lowest energy states. So these rotations, and if you can believe it or not, at room temperature, molecules like butane can change up to 10 times 10, can change conformations 10 to the 10 times, depending on the temperature and again the times. So they're continuously kind of rotating and basically moving between this state, this state, this state, this state, this state, this state. However, the most likely probability is to be in this trans configuration. Why? Because, well, the energy is the lowest. This, the highest energy state, is the least likely. These are more likely than B is more likely than C. Because again, you have these states where, look at, in C, the CH and H are eclipsing each other. It's not as bad as the CH3, but still, we want to kind of have our molecules be nice and separated out, just like we've kind of talked about in lecture. No one wants me to be kind of, invading their space. Now, next time we're going to get into structure, and one of the key kind of components of structure is this coordination number, or number of nearest neighbors. That's going to be a kind of a key idea. We're going to distinguish between different metals, polymers, liquids, gases, and this idea that if I have a lattice like we've seen in XRD here, right here, you can see that this atom here has 4 nearest neighbors. And then there's a larger distance, the next nearest neighbors, here. And then there'd be a largest next nearest neighbor, and then the next nearest neighbors, the next nearest neighbors. And so get looking forward to kind of looking and thinking about geometry, and hopefully have some artistic side, and you'll do well in the next section. So that's about it. So I look forward to seeing you, and we're going to get into structure next time. PCC, HTP, FCC, simple cubic. Get ready for that. PDFs, pair distribution functions. We're going to have a lot of fun. All right, I'll see you in the next video. Thanks.